In this video, we're looking at what appears to be a very complicated fluids problem. It actually turns out to be a very simple hydrostatics analysis to get it done. And there's a lot of words at the top. I'll just summarize really quick. We have a sealed canister filled with water. There's an air pocket above the water. Two tubes penetrate the lid of that container. One of them, the short tube, goes to the air pocket above the water. The other one goes 20 centimeters deep into the water. We hook up a vacuum pump to the short tube that's connected to the air pocket. And when that pump is turned on, we'll see the air go lower and lower in the long tube until eventually we get to a pressure that causes bubbles to come out of the end of the long tube. What we're trying to find is the minimum magnitude of the gauge pressure produced by that pump to get the bubbles to flow. And there are a couple basic principles we use in a hydrostatics analysis. One of the common ones is that the pressure in a column of air is practically constant because the density of air is so low compared to the density of water. And this means the pressure at the bottom of the tube when those bubbles begin to flow, well, that's connected directly by air to the atmosphere. So that's going to be atmospheric pressure. For now, I'm going to call the pressure down there PA, and we can say that PA is equal to 1 atmosphere or atmospheric pressure. And then, like with so many of these hydrostatics problems, we're just comparing 2 points in the connected fluid. And the other point of interest here is at the surface of the water, and I'll call that PB. And at that point, we have a direct connection through air to the pump. And so the pressure at point B is equal to the pressure produced in this pump. We then relate PB and PA through our pressure as a function of depth formula. So PA, that's the pressure at the bottom, is equal to PB plus rho GD, where rho is the density of the water, G is the acceleration of gravity, and D is the depth that we're going through that column of water. Now what we're trying to solve for here is PB, the pressure at the top of the water, which is the same as the pressure produced by the pump. So the pressure produced by the pump is PA minus rho GD. Since we're looking at gauge pressure here, we use atmospheric pressure as the zero of that scale. So the pressure at point A, it's equal to atmospheric pressure. On the gauge pressure scale, that is 0. And we end up with a negative gauge pressure because we have below atmospheric pressure produced by this pump. Negative, and then the density of water is approximately 1,000 kilograms per cubic meter. Acceleration of gravity is 9.8 meters per second squared, and the depth in the fluid is 0.2 meters. And we arrive at a gauge pressure of negative 1,960 pascals. And that's it. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.